Bismillahirrahmanirrahim. Welcome to the channel. My name is Asim Amjad, and in this week we start discussing the topic that is theory of beam deflection. The learning objective of this lecture are we will be able to derive the differential equation for the elastic curve of a beam. Then we derive the relationship between the load, shear, moment, slope and deflection of the beam. And finally we determine the maximum deflection of simply spotted beam while applying a concentrated load at the center. So let's start with simply spotted beam. On the one end is a pin and on the other end is a roller, and we applied a moment there. Then the beam would be bent at this shape. So here is an exaggerated shape when the loading is applied. Here we made some assumption, that is our material would be in linear elastic. We are considering the pure bending, mean the flexure under constant bending moment is applied there and no shear force, and the beam deflection due to shearing is negligible. So from our previous video lecture, we know that the moment curvature relationship, that is kappa, K is equal to 1 over rho, it's equal to M over EI. M is the moment and EI is the flexure rigidity. And we know that it's the resistance of a beam to the bending for a given curvature. So I am taking this equation as 1. And just to define what a deflection is. So deflection is basically the linear deviation of the axis under the bending. We call it as a deflection, and angular deviation of the axis under the bending is called at the slope. So here is the illustration of the above definition. Here we have a simply spotted beam, and when the moment is applied there, the beam is deflected at its center. So the distance at this point to this point is called it as y1, that is indicating the deflection, and again here is the distance of y1, that is indicated again as the deflection. So here you see the linear deviation of the axis and we call it as a deflection. And here if I made an angle theta at this point, the slope is meeting. So angular deviation of this axis we call it as a slope. We know that theta is equal to dy over dx. So from our elementary calculus, the 1 over rho is equal to d square y over dx square over 1 plus dy over dx square whole 3 by 2 power. So we know that the deflection of this element is really small. So we take this term as 0. So the square of this term would be the 0, and after rearrange the equation, that would be the 1 over rho is equal to d square y over dx square, and we call it as equation number 2. So from equation 1 and 2, we come with the differential equation for elastic curve of beam, that is EI, the flexure rigidity, times d square y over dx square is equal to bending moment, that is M, and it's a function of x as we are considering the non-prismatic load, that is varying. So if we have an equation for the moment along a beam, we can find the deflection by integrating twice and using the boundary condition to find the constant of integration. And the sign convention which we are going to use for the bending moment, we take this thing as an positive when the concave upward, mean the direction of the beam at like this, mean when the direction of the beam is like this, like a smiley face, we can say a concave upward, then we call it as a positive sign here. And if the deflection of the beam is concave downward, or you can say unhappy mode, then we take our sign convention negative. Mean d stair y over d at stair is positive at the concave upward, and d stair y over d at stair is taken as negative when concave is downward. So now we can find the deflection by integrating twice and using the boundary condition to find the constant of integration. So here is our structure that's undergoing a load and the deflection is take place. So let's start by first drawing the free body diagram of this model. So on one end you see a pin and on the other end you see a roller sport. And we have our load, a concentrated load at the center of the beam, that is P. And you can see the reaction force that's at upon this beam is shown here, that is P by 2 and P by 2 here. And the length of this beam is L, and as the load is applied at the center, so the distance from this point to this point is L by 2. So if you recall my previous lecture, we came up with this relation, that is negative value of the load at a point equal to the slope or the rate of change of the shear diagram. So minus u is equal to dv over dx. This is what our shear diagram look like. We already covered in detail how we can draw the shear force diagram. So if you didn't watch that video related to shear force and bending moment diagram, then first watch it. So at this condition the shear force diagram is shown here. So now again recall that from my previous lecture, and we came up with this relationship that V is equal to dm over ds, mean the change of bending moment between 2 points is equal to the area under the shear force curve. So we can now find our bending moment diagram. Simply take the area of this rectangle is L by 2 times P by 2, and that would be equal to PL by 4. So start from here, at this point the moment is 0 and plus PL by 4, and the second point would be like here. So this will be the straight line for the moment curve. And again, as the shear force is moving here downward, to just simplify or the maintaining the beam at its equilibrium condition. So here you see the shear, so here you see the moment is moving to the downward, mean PL by 4 minus PL by 4 would be equal to the 0. So this is the moment diagram of the simply spotted beam. The differential equation of bending moment, and it's equal to EI times d stair y over d at stair. So we take the derivative of this moment and we have the expression for the shear, and then we take the derivative of the shear again to come up with the expression of the load. So now we have some interesting relationship, and we can go in other direction by integrating to first find the slope, and the expression is shown here. So here we have an expression for d stair y over d at stair. If we integrate that, we come up with the slope, that is dy over dx, and that's shown here. So what I want to do now is I want to come up with what we are going to call the slope diagram, and the slope diagram is going to be the area under the moment diagram and will be changed in the slope. So you can see the area from this point to the center under the moment curve is PL stair over 16 because it's a triangle. So the slope of the slope diagram is start off at 0, and we know that the slope at the center is 0, so we know that the slope of the slope diagram is 0 at the left hand side, but it is increases because of the area under the moment curve to PL stair over 16. So we start off with minus PL stair over 16 EI, and we go to a slope of 0. Then we have a positive slope beyond that, going down to the slope of our slope diagram 0 out at the end, with again the change in slope being the area under the moment curve, which is PL stair over 16 EI. Then we can do the same thing for the deflection diagram, and it's the area under the slope will be change in deflection. As we know, it's a parabolic curve, so the area of this region is PL cube over 48 EI. So here is our expression, and we have integrated again. This is parabola in nature, so the area under the parabola is shown here, that is PL cube over 48 EI. So as far as deflection is concerned, we know that the deflection start off at 0 on the left hand side and 0 on the right hand side. So its slope is going to be negative value. So the slope of the deflection curve is a negative value, and it's going to change down to a value of minus PL cube over 48 EI. And then it's going to have a slope of 0 at the center. But it's going to have a positive slope at the end. So ending up with the total deflection of 0 at the end. So this is what the curve looks like, and we have integrated the parabola here. So we have a cubic equation here, and we now have an expression and a diagram of the deflection of this simply spotted beam with the concentrated load at the center. And we have the maximum deflection of a simply spotted beam with a concentrated load at center is PL cube over 48 EI, and we see that it's occurred at the center of the beam. So that's where we will leave off on this lecture. Thank you.